Hey everyone, my name is Shripad Patil, and today I'm presenting from Maple Grove, Minnesota. I'm going to be connecting Faraday's law of induction with Lenz's law of induction through a conceptual way to harvest energy. Now, this is something I wanted to research because it's been a question I've had ever since having a conversation with some friends a few months ago. Now, since people are pushing for sustainable energy more and more, we need energy sources that are green. For this, movement is one of the easiest things to exploit. Well, what's a common source of movement in our lives? Motor vehicles. 76% of American people use their car for their work commute. Now, because of this popularity, we might as well get a kickback from something we use anyway. This kickback's actually two-headed, though, because the install location gets energy, and people can get government incentives, such as tax credits. So what is induction? Being key to this project, it's important to explain this first. Induction is the process by which a voltage is generated through a changing magnetic field in a coil. Now, this is calculated by finding the rate of change in magnetic flux and multiplying it by the number of turns in the receiving coil. And this dictates Faraday's law, the equation of which is down there. Now, where does Lenz's law fit into all of this? Well, Lenz's law doesn't actually have its own equation, but it's the plus or minus in Faraday's law's equation over there. Basically, what it means is it governs the direction of the current produced by Faraday's law. Now for the design of a tunnel. So we need some way for the induction to happen. So we need a copper coil in the tunnel walls. So for this, we could potentially use copper tubing. Then we need magnets and vehicles. Additionally, we'd need an identification system for doing incentives, which would be through an RFID system or a camera-based license plate reader. Now let's move on to an example. This is a lot of math. Let's assume a 10-meter tunnel diameter with a 60-meter length and copper coils at a density of 6 turns per meter. That would mean 360 turns of coil along the tunnel's length. And let's assume cars are traveling at 26 meters per second, which is approximately 58 miles per hour. The first thing we do is we calculate this circumference of the tunnel, which is pi times the diameter, which is approximately 31.415 meters in our case. Now our coil surface area would be 31.415 meters times 360 turns to get us 11,309 meters. Now we calculate the magnetic field strength using permeability, turn density, and current. For our permeability, we're going to use 1 because that's the permeability of air. Then our turn density is 6 turns per meter, and the current is 200 amps, as that's the standard current for homes. That gets us a strength of approximately 15.0796. Converting this into magnetic flux, we get 1.7054 Weber. Now we find time. That's 60 meters divided by 26 meters per second, distance divided by speed, to get approximately 2.308 seconds for a car to travel the length of the tunnel. Plugging that into our Faraday's law equation, we get approximately 226 volts produced. Now moving on to considerations. Because of the magnetic nature of this project, it causes some restrictions. People with pacemakers, prostheses, or other medical implants cannot be in the tunnel because it just creates way too much risk for them. Additionally, joule heating is an issue. This is the method by which toasters work. It's running a current through a wire, resulting in heating from the internal resistance of the wire. Now, this can be fixed by using coolant in a low power pump, which is why I suggested copper tubing earlier in design. Now let's move on to viability, and this is the unfortunate part. This project is actually not that viable right now because we just need better technology to increase the efficiency of building because it just costs way too much and the return on investment is too long to be viable right now. And on that note, thanks for watching.